Deep learning sat in the academic wilderness for decades. Not because the ideas were wrong, because of a decimal point. Here's the setup. A recurrent networks loop is doing one thing over and over. Take an input, multiply it by a weight matrix, take that output and multiply it by the same weight matrix again on the next step. Same matrix again and again and again. To see why that's fatal, forget matrices for a second and just think about multiplying an ordinary number. Imagine a game of telephone across a massive stadium, except every time the message gets passed along, it comes out exactly 50% quieter. By the time it reaches the 32nd person, what do they hear? Absolutely nothing. Take the number 1, multiply by 0.5, repeat that 32 times, and you're left with about 2 ten-billionths of what you started with. It hasn't just gotten smaller, it's practically gone. Now flip it. Picture a snowball rolling down a mountain that doubles in size every single time it turns over. 1 times 2, 32 times over is 2 to the power of 32 or over 4.2 billion. It doesn't grow, it explodes. That exact arithmetic is what's happening inside the recurrent loop. If the values in your weight matrices are even slightly less than 1, repeated multiplication drags the activations and the gradients you learn from down towards 0. If those values are even slightly greater than 1, that same repetition throws them out toward infinity. After just a few dozen loops, the numbers inside the network are either astronomically huge or completely gone. That's the vanishing and exploding gradient problem. And this is where people push back. We run these models on massive server farms. The phone in your pocket renders complex 3D worlds at 60 frames a second. You're telling me a sophisticated AI gets defeated because the decimal point got a little too small for the computer to handle? Yes, that is exactly what I'm telling you. Because computers don't have infinite precision. Numbers get stored in an architecture called IEE754, floating point. The computer allocates a strict fixed number of physical bits, actual zeros and ones, to hold a number's mantissa and its exponent. So when a gradient vanishes and creeps down close to 0, the machine physically runs out of bits to represent that fraction. It doesn't quietly approximate. The architecture forces it to round down to absolute 0, and backpropagation multiplies every weight update by the gradient. Gradient 0 updates 0. The weights never change. The network flatlines, still running, still burning compute, and it has stopped learning entirely. Go the other direction and the floating point overflows instead. The weights swing wildly out of control, and the output becomes pure mathematical garbage, NaN, not a number. So this was never a compute problem. It's structural. If the architecture of the loop inherently causes the math to vanish or explode, all the compute power on Earth won't save you. And that leaves vanilla RNNs trapped in a vice. Don't truncate the backpropagation and you run out of GPU memory. Use the loop at all and the floating point math collapses underneath you. The escape came in 1997, a complete architectural redesign called the LSTM. That's where we go next.